Hi, welcome to the first video on the SAR ADC. In front of me here is the first part of this project, which is the clock. And there's not too much I can show you demonstration-wise because it's oscillating at 9 kilohertz, so you really can't see what's happening. But I can promise you it's working, and I can show you the screenshot from the oscilloscope that confirms that it is oscillating at 9.8 kilohertz with a period of 103 microseconds. So with that, I'm going to move over to the simulation because I think there's a lot more I can show you with that. This here is an online version of the clock circuit in Falstad, and I made it with transistors instead of inverter gates just because the inverter gates were being a bit buggy. I think that this Falstad demonstration has a lot to show about how this circuit actually works, and let's go into that a little bit. The important thing to know about how this circuit works is how capacitors work. At high frequencies, capacitors work just like wires. And this is important because you can see that current here is flowing through the capacitors from the high inverter to the ground of the low inverter. However, this can only happen while the capacitor still has enough charge because it's flowing through the capacitor. When the capacitor is out of charge, when it's sufficiently drained, then the state of the circuit will flip, and it will be the other side of the clock cycle. As a side note, I decided to run some basic tests with Falstad and determined that the frequency for this clock is relatively inversely proportional to both resistance and capacitance, and the frequency of the clock roughly follows this formula on screen. Note that capacitance has to be measured in farads, which is why there's a massive 20,000 in the denominator, but anything in the farads is going to be a super small number because you're generally using capacitors that are 0.1 microfarad or maybe a few microfarads. Moving on, let's discuss how an SAR ADC works in general. An SAR ADC stands for Successive Approximation Analog to Digital Converter. The second part of that is pretty straightforward, but the first part is not. Successive Approximation Register is a type of an ADC that essentially zeroes in on the value of the analog signal. Here's a block diagram of what an SAR ADC looks like. You can see that it starts with the analog signal going through a sample and hold circuit, which does just as the name says. It samples the analog signal and holds it for the duration of the conversion, which in this case, for our 7-bit ADC, is 8 clock cycles. This held signal is then compared to the output of a DAC. It may be a bit confusing why there's a digital to analog converter inside an analog to digital converter, but this becomes clear once we discuss how an analog to digital converter works. Essentially, it works by trying multiple different analog values produced by the DAC and comparing them to the sample voltage from the sample and hold circuit. And depending on the output, the next test value of the DAC is altered to zero in on the real analog voltage reading. So essentially how this works is the circuit very algorithmically approaches this problem. It starts with half the supply voltage, which in this case is 2.5 volts. It will compare this to the sample voltage, and if it's higher, it will go up the range, and if it's lower, it will go down the range. What that means is that if the result of this comparison is 1, meaning that the sample is higher than the 2.5 volts generated, the next generated voltage by the DAC will be in the middle of 2.5 and 5, which is 3.75. If the output of the comparison is a 0, meaning that the sample voltage is lower than the DAC, then the next test voltage for the DAC will be a 1.25 volts, which is in the middle of 2.5, which is the original test, and 0. This process then continues where the middle voltage of the determined range is used as the next test voltage. For every comparison, the value is stored in the SAR, or Successive Approximation Register. This register holds the final result for the digital or binary representation of the analog voltage. In this timing diagram, you can see the DAC essentially, again, zero in on the target voltage, and you can also see when the bits are set in the SAR. While in some block diagrams, you may see that the SAR goes directly into the DAC, it's important to note that this isn't exactly what happens, and there is some logic to determine what bits are sent into the DAC. However, we're going to keep this at a general overview. So with that, that's how an SAR ADC works, and that's the clock used for this SAR ADC. Thanks a lot for watching.